Okay, so this is our project, Computer Vision-Based Deforestation Detection for Environmental Conservation. And these group members are Ojok and Honey and me. And very shortly, our project is to train these AI models to detect deforestation in Uganda. And we will get back to the objectives and the goals, but that's short what the project is about. And we have been looking at a lot of different related works that have also involved deforestation, either in other countries or with other models. And firstly, this first article, deforestation detection using deep learning-based segmentation, semantic segmentation, they have looked at, that's also the reference that is in the bottom here, and also the figure. They have been looking or summarizing a lot of different research on deforestation. So they have been looking at what models have they been using, what has the results been, and overall, as you can see in the histogram here on the side, UNet is the most popular model for deforestation detection. And they have a lot of, most of them are also convolutionally based, but they have a lot of these other models that are evolving that are also having very good results. And then secondly, we have this crowd-driven deep learning. They use 3 different models, VGG, a ResNet model, and a CNN model. And then the ResNet model is the one performing best in their case, but they don't apply any explainability or interpretability. The third one, vision transformer model for convolutional free multi-level classification. They look at the different causes for deforestation. So they investigate if it's agriculture, urbanization, infrastructure, what is affecting or what is the main causes of deforestation, so that they could detect the areas that are likely to be deforested. And lastly, this article, it is not very good. It looks like it's made by students. But it is quite interesting because they do what we intend to. They are taking these different deep learning models and they are using different explainability and interpretability techniques to see what is overall the best model. And that is, we'll get back to that, but that's also what we want to do. And we have looked at a lot of different other related work, and all of it is in paper. And overall, also SHAP-LIME, ShapeHash, and eLife5 is also the explainability and interpretability techniques that are most commonly used when we look at the other work. And then the reason that we want to investigate this is that deforestation is one of the main causes of destructive phenomena as biodiversity reduction and climate change. And Uganda is one of the countries with a lot of diversity in species and forests. But Uganda has also lost 40% of its forest cover in the past 100 years. Now the forest cover in Uganda is historically low at 12%. But the politicians has also said that they want to restore this. But then it's important to know the causes of deforestation, the extent of it, and also see if these models can be interpreted and explained.
Thank you very much, Ms. Sister, for taking us through that. I'll be taking you through the research questions and objective parts, and some of the research questions that we have when we're building this model, why we came out to build this model for deforestation detection. One is future representations, where we're actually asking ourselves, how can we get relevant futures from satellite images that can help us detect deforestations? Then another one is model generations. How can we build a model that generates it and give accurate information on different for example, you have different land use, land cover, you have different activity pattern, let's say wetland, and all those can use all those images and generate it and still give predictions. Then we have the real-time or near-time processing. Now, most of the data, the models that are built, they don't have to give real-time images. So we were trying to look like, how can we build a model which can give a real-time or near real-time images based on the current images that have been put in. Then the data quality, we are looking at how can we access or make data be accessible for building a best model for detection of deforestation. Then some of the objectives that we have is one was to detect areas in Uganda where deforestation has occurred and understand the background on which the models give this output, like develop a model and understand the interpretability and explainability, which most models don't have. And then another thing is to distinguish human-caused deforestation from natural causes of deforestation. If deforestation has happened, so what? What have caused it? Is it human being or is naturally caused by fire, maybe on the desert? We need to detect that. And to detect deforestation on real time or near real times. I've already talked about this. I'll discuss later. Then some of the research contribution that we believe we have added to this project is we developed a GradCam for interpretability of our models. This one helps us to interpret the model. Then we also develop explainable deep learning models, which others are not there. Our model is able to be explainable using Lime, Sharp, and then GradCam for interpretability. Then we develop models that detect deforestation specifically in Uganda because the data we use, most of them can cover the world, which is not efficient, but ours is specifically Uganda as a country. Then when you look at the methodology used, first of all, we use the data set. The data set we got from the global forest change. And then from that data set, you are able to pre-process it by cropping it from using QGIS, where we cropped it into 100, into 10 by 10. And then that data set was, it has actually 6 layers. It is our data set, and we have 6 layers of that data set, which we later on tiles it into a 100 by 100 pixels. This is a sample of the pixels which have been styled. Then we created around 3 models we are working, the recurrent, unit, and then CNN. Then we do model evaluations. Then some of the models, like unit, needed us to resize the data set, which we resize because it needed 240 by 240. About the model evaluations, one of our colleagues will talk about it further, but this is our methodology, which starts by getting the data set, cropping it from actually the data set we use is this Ancient data set. We cropped it. It has 6 layers. We tile it, then we pass it into the input through the model, then we evaluate the model. Basically, that's what I've prepared for you for today. Thank you very much. Another presenter will take us through.
Good evening, everybody. My name is Hani Abdurrahman, and I'm going to continue from where my colleagues have stopped. Below shows you the methodology that we have used. Basically shows you the summary of how our work was flowing. Firstly, the data set is we have the data set called the Global Forest Change from Hansen et al. And others. This data set has 6 different layers, each of different relevance and importance because of the different features that it gives us. Examples of them, we have like the tree cover, the grid layer, then we have the loss year grid, first layer grid, last layer grid, all of different importance. What we did with that is we broke them down into tiles of 100 by 100 pixels, and then we worked on them using the different models. In this case, we used convolutional models, of which there are 3. Moving on to the next slide. Below shows you the results and the explanations of the work we got, the results we obtained. Firstly, the one on the right shows you the GradCam of the unit. The one on the left shows you the GradCam overlay. That's a difference of overlay image of the CNN. So the one which is bluish, that's now the GradCam heat map overlay of the original image. So how did we come up with this image? Firstly, the original image is obtained, and then the GradCam is generated. GradCam meaning the gradient weighted class activation maps, and then the GradCam and the original image are superimposed to create this overlaid GradCam heat map. All right, GradCam heat map, overlay heat map image. All right. So the GradCam works by showing you the areas of the input image that are of relevance to the model, helping the model predict the results that we had obtained. And then explaining the GradCam image of the unit on the right. In this case, it shows you the areas that are of relevance that are important to the unit model. Unit uses a discriminator and a generator. So it uses those two functions to work on the input data. How is GradCam obtained? GradCam is obtained using two inputs, the model and the input image, processing them in order to obtain this current image. Here we have on the first column, we have the activation maps of the different layers of the CNN. Second one shows you the activation maps of the units. So for the first one, you can see how it is visualized, how the activation maps are visualized, showing you how the different layers give you different kinds of images. And then the second one shows you how it is also obtained. For the second row, this is applied to the unit model, and the unit model uses 12 different convolution layers, starting from convolution 2D layer 25 to convolution layer 2D 37, and each of them give you different outputs when you run them through the model. So there are some elements of the different layers that are important to us in this case, and this is what we obtain. Then the conclusion we have is the unit is better overall because of its explainability. It has an accuracy of 69.9%. CNN has an accuracy of 82%, but unit also has a better specificity that is around 99%. And because of the explainability and it aligning with our goals, we have actually decided that we shall go along with the unit. The limitation is that our model is not real time because we're using recurrent neural networks, and obtaining real-time images from satellites is actually a really difficult thing. The previous researchers have only been able to obtain near real-time images, not absolute real-time. We need more explainability techniques for comparison. We only use full scope images. There's been polarization of some of the datasets images that we have had. Deforestation detection can only take place in higher resolution. And so we want to improve this and make it detectable on a smaller resolution, can differentiate between human and natural deforestation, large data-based storage required. Real-time detection recommendation is as given below. We want to acknowledge all these people here for their work and their related works and for helping us obtain the dataset that we have. Thank you so much.